Hi, my name is Manish Gupta, and in this video, I'm going to talk about how to interpret stable diffusion kind of model using cross-attention. In fact, this follows a methodology called as DAAM or diffusion attentive attribution maps, and this is also one of the best papers at ACL 2023. So let's get started. What are diffusion attentive attribution maps, right? So how does the method work? So it is broadly based on latent diffusion models. Just to give a very basic introduction to this video, in this video, I'm going to talk about actually answering this very intuitive question. How does an input word influence parts of a generated image, right? So there have been so many image generation models recently, so like Stable Diffusion and so on, DALI 2, and many others, right? So when they generate these images, you can actually condition them on a text caption, so text input. So how does an input word influence parts of a generated image? Right? So they are all based on this latent diffusion model methodology, which basically has three parts mainly. So one, there is a clip model, which is essentially an image or a text encoder. In that sense, is when you pass text, you need to encode it somehow. That's basically an encoder, right? VAE, so which basically has an encoder and a decoder part. So essentially it takes images, encodes them to latent vectors, or takes latent vectors and decodes them to large images, right? And then there is a unit. So as you see, this is the unit part. This is the unit part, which basically takes a noise vector and then gives you a latent vector, which can be decoded into an image, right? So using latent diffusion models so as to generate an image, it basically contains the following steps. So you first initialize the latent vectors, this one to random noise. You start with random noise. And this random noise basically could be of width W and height H, right? So essentially that's L0, the latent vector at 0th time point, right? And then you feed in a text prompt as well. So you could, of course, you could these days condition on various kinds of things. In this particular work, they are looking at text. So you can actually feed in the text prompt. Of course, you do some text embedding and you feed in the text prompt, right? The third thing is you iteratively denoise the latent vectors with unit. So what you see here is basically unit, and this is done iteratively. So as you see, basically you do this for t time steps, right? The final decoded vector which you get, this is the final decoded vector Z that is obtained here. Basically, you pass it to the decoder of the VAE, and that gives you the decoded image, right? So that's how a typical latent diffusion model works. And this paper is about understanding, if you basically give a particular word in as part of this text, what kind of outputs, what kind of changes do you expect in the image that gets generated? Right? So to be able to understand that, of course, they look at attention maps, right? So what kind of attention maps is the question? Now, as you can understand, unit is a U kind of a model. So where you start with a latent image and then you do downsampling, 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 until you're left with a very small vector or a very small 2D image right there, which you then upsample, 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 so as to basically get an image of the same size, right? So while doing this downsampling and upsampling, essentially what you're doing is cross attention. So when there are images, when there is this conditioning text which comes in from the bottom, right, you essentially do cross attention here, right? So essentially in every upsampling, downsampling operation, there is cross attention which is participating, right? So so essentially, this is basically some, the equation shown for the downsampling part. So when you are downsampling the hidden layer output, remember there are two indexes here, I and T. So here T actually stands for the time. So essentially, as I mentioned, you'll be doing this unit kind of an operation, denoising operation, T times. So, if you don't understand diffusion process and this diffusion model, I really motivate you to look at the latent diffusion model videos that I've created in the past, right? But anyway, so, you do this unit kind of processing T times. So therefore, this T is for that. And then I is basically the ith downsampling layer. So the ith downsampling layer, what you do is to basically you compute cross attention. So the way cross attention is computed is exactly mentioned here. So essentially, you first compute the attention weights, which is given by this f function, and then you multiply by the value matrix, right? So the value matrix is computed on the x. X is the text embedding here. So x is the text embedding. So on that, you compute the value matrix by multiplying a WV of I. Of course, you have a different, weight matrix for the values, keys, and query key and value for every ith layer. However, those matrices are shared across time, right? So that's that. Now, when you do this, you essentially get the overall H, which is basically the next it's hidden layers, downsampling hidden layers output. Okay. Now, while computing this, you're of course using these attention weights. The way these attention weights are computed is in the standard transformer way, but then this is cross attention. So as you notice, this attention, the query part is coming from the hidden layer, but the key part is coming from the text, right? Similarly, the value part is coming from the text. So that is how cross attention is computed. Okay. Now, as you notice, this F basically is cross attention. So it sort of tells how much attention a particular part of the image is basically part of the image, right? Because this is the output from the previous layer. So how much attention a part of the image is paying to a particular part of the text, right? A particular word in the text, right? So essentially this F that you see, whether it is for upsampling or downsampling, well, its size is given, it's a 4D tensor, right? Its size is given as the downsampling factor, or rather, the width of the downsampled image or height of the downsampled image. And then LH stands for number of heads. Basically, of course, this is the multi-head self-attention, so you could have several heads, right? And then LW, which is basically standing for the size of the overall text, right? So now, of course, you have these Fs for every time. First of all, there are, as I noticed earlier, there are like T time points in the diffusion process. There is also a attention map for every layer. So ith layer from I equal to 1 to k, if there are k layers, right? And also there are upsampling and downsampling attention maps, and that is how you basically have like FTI upsampled and FTI downsampled, all of them, right? Now, the way this diffusion attentive attribution maps works is to basically come up with an aggregation, spatial temporal aggregation, as it is called, over all of these all of these attention maps. Now, if you notice, right, for layers which are far away from the original image, or closer to the center of the unit, right? For those layers, the overall attention map is going to be pretty small. So therefore, you have to essentially do bicubic interpolation so as to expand them to be able to be of the same size as the original image first, right? So these are called as intermediate coordinates, and you map them to a square in the final image, right? So, and after you've upscaled all of these intermediate attention scores to match the original size of the original image, you essentially just sum over different heads, different layers, different time steps, so as to get essentially a single attention map, right? And you of course also combine across the forward layers and the backward layers. So this is how essentially this aggregation is being shown. You combine across I, J, and L, right? Where you're combining across heads, layers, and time steps, all three. Okay. So that basically gives you a nice attention map, which is of the same size as the original image, and that tells you how much attention every word is paying to every XY pixel in the original image. Okay, so that's how this attention map works. And then this is the output of a particular attention map. So here is an image, and here is a word monkey, which was there as part of the prompt, or hat and walking. As you see, monkey basically pays a whole bunch of attention to the face of the monkey, hat pays attention there, and walking, of course, pays attention to the walking. I mean, since the legs part and so on. Okay. Now, these attention maps can also be binarized. So, of course, you can take the heat maps, and then you can basically have a particular threshold beyond which you can say, hey, the particular pixel is activated by this particular word in the text, while it is not activated in the other case where the attention value is less than a particular threshold. Okay. So how can you use this? So you can use this for various interesting analyses, which is what is the major interesting part of this paper. It's about so the first experiment is about object attribution and generalized attribution. Okay, so the experiment with the Stable Diffusion 2.0 model. Okay, so Stable Diffusion model, and then so what they do is to first check if these attribution maps that are created, and if you basically do segmentation using these attribution maps, does it give you really as good segmentation as doing segmentation on the original image itself? Okay, so they essentially take some Coco captions and they synthesize images, generate images using Stable Diffusion. And for ground truth, basically they extract all countable nouns from the caption and ask people to create segmentation maps. Okay, so they don't depend on any segmentation algorithm. They actually ask humans to create segmentation maps. And then they compare the segmentation as provided by their particular model. It's called as the DAAM model, DAAM model, right? Versus the human segmentation map, and they compute mean IOU, so mean intersection over union, over 80 classes. So the COCO data set basically has many classes of nouns. So they compute it over those 80 classes or over infinite number of classes. So why these 80 classes? Because, well, these supervised models are majorly trained on these 80 classes only. And infinity basically just means that, hey, you care about every noun which is mentioned in these captions, irrespective of whether they belong to the same 80 or not. Okay. So what is observed? So they compared several other models. It is observed that well, supervised models are, of course, much better compared to non-supervised methods, right, for image segmentation. However, the most important part is that amongst the unsupervised methods, their method does the best job, which basically means that their method is able to capture the natural segmentation which is present in the image, right? So this attribute analysis method, the diffusion attentive attribute maps method, is able to capture the natural segmentation. Okay. Now, they repeat the same experiment for not just nouns, but other part of speech tags as well, like numbers, adjectives, adverbs, and so on. And in this particular case, creating segmentation maps does not make sense. For example, if somebody asked, hey, tell me in this particular image, what is quickly, right? Create a segmentation map for quickly. It's sort of very difficult to do that. Okay. Therefore, what they did was to basically create these heat maps using this attention analysis and then showed it to people. And they asked human raters to rate, hey, what do you think? Is this part of the image which is highlighted really mapped with the word that was supposed to show, right? And what they found is that for a whole bunch of part of speech tags, all the 6 part of speech tags that they considered, humans rated, that heat maps to be somewhere between fair and good, right? So in some cases, in fact, it was between good and excellent as well. You can actually see some really good cases here. So for example, here the number 3 is highlighted. And for the number 3, you can actually see that the giraffe's edges are actually getting super high attention values, which indicates that, yes, it has been able to figure out 3 giraffes, right? Similarly, for this particular query, it is an adverb-based query quickly. And then as you see for the word quickly, essentially, the feet and the ground motion blur is essentially being highlighted, which is actually the right notion to denote quickly. Right? Blue, again, in this original image, the teacup is blue and therefore that teacup is sort of highlighted. Running, if you look at running, well, the fists and the legs which are sort of involved in running are sort of highlighted. Similarly, for proper noun like Eiffel Tower, of course, the Eiffel Tower part is highlighted. For oranges, of course, the oranges part is highlighted, right? So essentially saying, yes, the attribution analysis gives very good results from segmentation analysis perspective. Okay. Now that it's a more interesting analysis, like, how can you represent pairwise dependencies across words and text in terms of dependence, in terms of what you see in the images? Okay, so that's the interesting experiment. So what they did was to essentially was to do dependency parsing using core NLP. So they took some captions, did dependency parsing on core NLP, generated images around them, and then did some further analysis. Okay, so what was the analysis? So as you may know, dependency and parsing in core NLP essentially gives you several kinds of dependencies between pairs of words. So the 2 words which are participating in this pair are called as head and tail, or head and dependent. And then these are some of those dependencies which are popularly observed in text based on dependency parsing, right? So compound nouns, for example, punctuation, this is and kind of conjunctive dependencies between 2 words, determiner, case, and so on, and subject dependency for noun, subject, adverb, adjective modifier, object dependency, and so on, right? So several dependencies are highlighted here. Okay. So what is shown in this picture are various metrics, 4 different metrics which are shown here. So let's try to understand what those metrics mean. So what they did, what did they do with the dependency parse things, right? So they took captions, did dependency parsing. For every dependency, you have a head word and you have a dependent word. And then what they did was to look at their heat maps. So they created these heat maps for both the words. And then they basically, computed, 4 different, so these 4 different values that you see here. And, the way they calculated is as follows. So of course, they calculated the intersection, so which is basically intersection over union. So that's one of the simple things that you can calculate, intersection over union. They also computed intersection over dependent and intersection over head. So which is sort of obvious. So if you consider this as the head and this is a dependent, so this is basically intersection over dependent, right? So since this was the head and this is the dependent, this is intersection over head. And so what they did was to basically look at this. The difference between intersection over head, intersection over dependent, right? So if intersection over dependent is greater than intersection over head, it sort of means that head dominates the dependent in that sense, right? So in the semantic meaning, which is expressed in the image. Okay. So now with that understanding, right, let's try to get to the fun stuff. So the fun stuff is as follows. They found that rows 3, 4, and 6 show no dominance. So let's basically look at these, right? Compound nouns, punctuation marks, and determiners, they show no dominance. So no dominance means, these scores are, if you look at this guy, and this guy, um, especially if you look at these scores are very close to 50s, which basically means there's no obvious dominance of either the head or the dependent, right? Row 5, if you look at row 5, so conjunction. So one interesting thing to observe is that the intersection 38.2 is pretty low. And there'll be more details about why this is pretty low on the next slide. Okay. But that was what was observed, that the intersection between these two things is pretty low when you're using conjunctions. For example, if the caption was zebras and horses eating grass, right? So then either the image had zebras or grass or horses, and therefore the intersection was pretty low from that perspective. Okay. Now the other interesting parts which you see here, and which also expressed in the image, by the way. So I'll also talk from the basis of from by looking at image. Verbs contextualize both the subject and the object. Okay. So and this is denoted, by the way, using the in-subject dependency here, because in-subject dependency is between the noun and the verb, and obj dependency because that's also dependency between a verb and the verb and the object. So in-subject is between verb and subject. Obj dependency is between verb and object. So what you see here is that the difference, if you notice the differences, they are pretty high, right? So 12 versus 29, or rather 12 and 29, right? Versus the differences that you see, in these particular cases. So the differences in, 3, 4, and 6, these differences are so little, right? Versus 12 and 29 kind of difference that you observe in sub J and obj, right? And what this essentially means is that, yes, the verb guy essentially dominates significantly. The verb guy dominates significantly compared to the noun, with either the subject or the object. Now, you can observe that here as well. So bird stands, those were the two words. And then if you notice the heat map for stands, it's basically much larger compared to the heat map, the activated heat map for the word bird, right? Similarly, if you look at veering, the heat map is much more stronger for the verb compared to the heat map for the noun shirt, right, or the object shirt. Okay. So, and that basically means that when you're trying to express the meaning of a particular phrase, whether it is a noun verb, an n subject phrase, or a verb object or an obj phrase, you basically observe that the verb basically is denoting is trying to capture lots of semantics from the image. Okay. In collective nouns, similarly, the domination was observed uh, in the collective noun part. So, if you look at pile of oranges, so essentially you have pile dominating the heat map. Similarly, when you looked at descriptive adjectives. So descriptive adjectives actually dominate the nouns. For example, in this particular case, wooden bench, you see the heat map here is much more stronger than the heat map just for the word bench. Lastly, co-referent word pairs. So for example, man and his, if you look at the heat maps, they are practically very, very similar, leading to a significant intersection over union. So leading to a significant overlap between the heat maps created for the head and the dependent words in the dependency, right? The last analysis that they do, interesting one, is visio-semantic analysis. So what is visio-semantic analysis? So they took words which are hyponyms, first of all. So cohyponyms, as they are called, which basically, so an example is a giraffe and a zebra, right? So giraffe and a zebra are cohyponyms because they both belong to the same node in WordNet. So if you look at WordNet is a network of concepts, right? And words are arranged in a hierarchy. So giraffe and zebra are both, let's say grazing animals, and grazing animals are in general animals, and animals are, organisms and so on. So there's a hierarchy that WordNet has. And if you look at giraffe and zebra, they are at the same level from the two top root node of the WordNet graph, right? So if you took those, co-hyponyms, you can call them as co-hyponyms. So if you look at co-hyponyms, and you take those captions and try to generate images, what you observe is that, so these are all images which are shown, which are generated for the phrase a giraffe and a zebra. And you observe that the generated images either have a giraffe or a zebra. Now that's so odd, right? And they observe that this happens especially for co-hyponyms. Now, if you generated images like for phrases like fridge and a giraffe, or fridge and a zebra, you would still see both the objects. So non-co-hyponyms is okay, but if you put co-hyponyms, they observe, for a lot of cases, that the image that the model, Stable Diffusion model, chooses to show one. Okay. Now, which basically is this conclusion that semantically similar words in a prompt have worse generation quality, where only one of the words is generated in the image, not all. Right? And again, if you sort of compare the intersection over union for cohyponyms versus non-cohyponyms, you observe the intersection of over union was much higher for cohyponyms versus for non-cohyponyms. So not just that you observe that the quality of stable diffusion models is really poor for cohyponyms, you also observe that for cohyponyms, the overall heat maps actually also relate a lot, right? So basically, and that is why, in fact, the model sort of feels that it has already done the job. So it sort of feels that, hey, if the caption was a giraffe and a zebra, well, if you look at the heat maps, giraffe and as well as the word zebra have the same heat map, almost the same heat map, although, giraffe and zebra are two different words and the image is exactly the same. So the stable diffusion model feels that it has done its job by sort of drawing the giraffe when it should also have drawn zebra. Okay, so that's that. So um, they do further analysis, between of accuracy, further analysis of accuracy. So they ask humans, by the way, to essentially label these generated images and then identify if it basically generated both giraffe and zebra, right? And they actually do this for several such pairs. So what they find is that they look at accuracy from these perspectives. If the input that they gave had cohyponyms or non-cohyponyms, they always give pairs of nouns in the input, okay, input prompt. And then they also look at the other axis, degree of overlap. So how much overlap was present in the heat maps for these words after you look at these attentive heat maps, right? So they found that the best accuracy, and what is depicted here in the 6 cells is the accuracy as judged by humans, right? So they find that the accuracy of the generation is super high when you are trying to generate images for non-cohyponym captions, and also when the heat maps have low overlap, okay, low overlap. That's a very interesting observation. But they also had other interesting observations. So they had this interesting observation that if you sort of try to come up with images from stable diffusion, where you just change the adjective in a noun. So for example, red colored car on a road, red colored car on a road, versus a blue colored car on a road, or a green colored car on a road, or a red colored car on a road. What you observe is that it's not just that the car becomes blue, but you observe that this other surroundings, and this is a zoomed in version of that surrounding, or other surroundings here. This is a green zoomed in version, this is a red zoomed in version. It's not the zoomed in version only, it's also a highly saturated version, so as to show that not just that the car gets blue, but also the surroundings become blue. So the color sort of overflows to the surroundings as well. Now, sometimes it may be expected, sometimes it's not expected. For example, why would the building be blue if the car is blue? These two have to do nothing with each other. However, on the other kind of settings, if you basically are looking at this rusty kind of stuff, of course, if you have a rusty kind of a vessel, right, it must be occurring in rusty places. So it's okay if it occurs in rusty places, right? But a car occurring in front of a building which is blue in color is, this doesn't make sense. But this is what they observed happens, when you are using stable diffusion models to create images. And this is a great visual semantic analysis coming out of this attentive diffusion analysis based model. So anyway, so in this video, I talked about the DAAM model, which is essentially the first work to interpret large diffusion models from a visuolinguistic perspective, right? And the major, the most important question that the model that this interpretability analysis attentive heat maps, the most important question that they try to answer is that which parts of the generated image the words influence the most. So if you have a text caption and you have a generated image by these models, which part of the text caption, which word essentially influenced which particular part in the image that was generated. Okay. The other kinds of questions that they try to answer as part of this work is how do syntactic relationships map to generate pixels? For example, if they're numbers, what kind of pixels basically get activated a lot, or they get generated to showcase or to reflect that number in the caption. If they're adjectives, adverbs, which part of the images get generated to reflect the semantics of those adjectives or adverbs in the text caption, input in a text caption. Okay. Okay, so that's it for this video. You want to look at the code, you can actually go ahead and look at the code there. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage.